Okay, so on what day was that? Was it Thursday online that we started 6-1? Oh yeah, Sarah has a question. Good. Can we go over number 39 from 5-5? Absolutely. Let me pull up my book. Hold on, give me just a second here. Let me pull it up. Actually, give me 1 second, Sarah. I need to grab something. I'll be right back. And Adam, I'll be right back. So we're going to do 39 from 5-5. I'll be right back. Can you show me at lunch? Okay, sorry, I'm back. My book was downstairs. That was not so helpful. All right, so number 39 says, use the half angle formulas to determine the exact values of the sine, cosine, and tangent of the angle. And so we have 15 degrees. Okay, so let me write on here. Maybe. There we go. Number 39. We have 15 degrees. We want to figure out the exact measure. And they're telling us to use the half angle formula, right? So really what they want us to do is to think about 15 degrees. What we're using the half angle formula. So 15 degrees is the halved angle. So really what we can do to figure out 15 degrees, we can use 30 degrees, the values of 30 degrees to help us figure out what the measure of 15 degrees is, because half of 30 is 15. Okay, so then if you pull out your half angle formulas, let me see if I pull them up here. Somewhere under here. And by the way, oh, hey, Jennifer. We're doing number 39 and 5-5. And if you haven't looked at your test yet, and I did see, Jennifer, at the end of the last call, you asked if you can use a unit circle. You can use the unit circle, and then I gave you a page of formulas. So I'm not expecting you to memorize, for example, the half angle formula. Goodness gracious. I'm just expecting that you can use it. So I just opened and closed it. It's kind of how the day is going. Is everybody glad to sleep in today? Are your other teachers making you have class online? Probably not. Okay, so here we go. If we want to find for example, if we want to find the sine of 15 degrees, right? And we want to use the half angle formula. And we look over there. Basically, 15 is like u over 2. So 15 degrees has already been halved. So that tells you that our u value is 30, which is really helpful because that is one of our values on the unit circle that we can easily evaluate, right? So if we look at the half angle formula, the sine of u over 2 equals plus or minus the square root of 1 minus the cosine of 30 degrees divided by 2. So this works out nicely because cosine of 30 degrees is something that we can look up on our unit circle, right? So I have a unit circle in front of me, and when I look at 30 degrees and the cosine, I see that it is the square root of 3 over 2. So I would say plus or minus 1 minus the square root of 3 over 2 all over 2. Okay, and so then we have to do some simplifying, right? Plus or minus 2 over 2 minus square root of 3 over 2 over 2. So I end up with, I don't have a lot of space here. There we go. I end up with 2 minus the square root of 3 over 2 over 2. And all this is square rooted, right? And then I can move the denominator of my top fraction into the denominator of the bottom fraction. So I could write this as 2 minus the square root of 3 divided by 4. Take the square root of that, plus or minus. And I think technically what we could do is then we could take the square root of the top and the bottom, since 4 is a perfect square, and we would say it's plus or minus the square root of 2 minus the square root of 3 divided by 2. So that's what the sine of 15 degrees would be. That makes sense, Sarah? Okay. Do you want to see the cosine and tangent? I can do them or not. It's up to you. Okay, cool. Yeah, I think the tricky part's kind of figuring out, oh, they want me to take the sine of 15, but that means that that is the half angle, not the full angle. Cool. All right, so today, like I said, I want to go over, we're probably just going to go over a little bit more of 6-1 today. We'll see if we get through all of it. We talked about this online on Thursday. I was hoping to talk about it in person, but we're using this law of sines in order to, so let me take a step back. Chapter 6, the new piece of information, or the new way that we're going to figure something out, is what happens when we don't have a triangle, when we don't have a right triangle. We still have a triangle. When we don't have a right triangle, can we still use sine, cosine, tangent, our trigonometric functions, to help figure out our angles and sides of triangles? And the answer is yes. It just looks a little bit different. So we talked on Thursday about the law of sines, which is just basically the set of ratios, right? We have side A over the sine of A is equal to side B over the sine of B, which is equal to side C over the sine of C. And this is true for oblique triangles, which basically means not right triangles. So we could have an acute triangle or an obtuse triangle, and the law of sines work. So what I mentioned on Thursday online is that this works really, really well for triangles where they give you the angle and the side. It also works for triangles where they give you the two sides and an angle, but it gets a little bit more tricky. And so we're going to talk about that today. And I wish I'd meant to do this. I wish I was a little more high tech and had a drawing board on here, but so let me find one that is that case. All right, so if you have, okay, so there's a little kind of drawing here about these different cases and what they were. Oh, I'm sorry, Jennifer, I didn't even see that. Do number 9 and 11 from 5 at the end. Yes, absolutely, I can do those, Jennifer. I will save time for those. Sure. So there's this ambiguous case of side-side angle, and we can talk about what this picture means, but I think if we do a problem, you'll be able to kind of visualize what exactly they're talking about. So problem number 8 is what we're going to do. They tell you that angle A is 60 degrees, side A is 9, and side C is 10. And they want you to figure out what the other angles and sides are for the triangle. So you might hear it being said that you need to solve the triangle. So what we want to do, pull up and paint. I'm going to try to do a good job with my drawing here. So we know that angle A is 60 degrees. And we know that side A is 9. And we know that side C is 10, I believe. Yes, 10. Okay. Side C is 10. So if we kind of map out what this triangle could look like, right? We know, try to do a good job drawing 60 degrees. Maybe needs to go a little higher. It's between 45 and 90. I still feel like that's 45 degrees. Come on, paint. Why aren't you fancy with... Sure, we'll make that 60 degrees-ish, right? So we'll call this angle A. We know it's 60 degrees, okay? We know that the side opposite this is 9, right? So there's a couple different ways, and then we have B, right? And we have C, point C. So side A is somewhere over here, right? Side C is 10, and side B, we don't know what that is. But the thing we don't know is, how is side A drawn? Okay, so you could have, and I didn't even make my triangle big enough. Hey, Aiden, how are you? So if I were to draw side A in, I could actually draw it like, if this is 10, I could draw it like this, and it could still be 9, right? No problem. Or I could draw it like, I'll try 2 different colors. I could draw it like this, and it would still be 9. So I don't know if I'm doing a great job with my drawing, but try to visualize in your head. If you know that this has to be 60 degrees, this side is 10, then we don't know if B is shorter or longer. And if this is an acute triangle or an obtuse triangle. And actually, in cases like this, where they give you an angle and 2 sides, we can use the law of sines, but we actually can have cases where there's more than one solution to our equation. Okay? So let's see how that kind of plays out with the math and how we figure out what the angles are. So I don't know if you can kind of visualize that. It's a little bit of a weird concept to think of, but let's see kind of what we can come up with. So what I'm proposing is that we have one triangle where this is A. I still want to draw that at 45 degrees. I don't know why. We're doing number 8, and we're doing number 8 on the example page. So this is a 60-degree angle, right? This is 10, okay? This is 9, and this is angle B, and this is side B, and this is angle C. So we could have an obtuse triangle, right, that would kind of hold this case. And then we could also have a triangle that, again, is 60 degrees. This is 10. But instead, my side across from my 60 degree, the 9 goes this way, right? And I know this is not perfectly to scale, but the side goes this way. So this would be 60 degrees. This is 9 again because it's across from angle A. We have B, C, and side B. So are you guys kind of okay with the idea that we could have two, just based on kind of drawing it, right? So how do we figure out the math side of what the two possibilities are? So we're going to use the law of sines, and the law of sines is the same no matter what. So we have, side A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C. Okay, we know that A is 9, and the sine of A is the sine of 60 degrees. So let's fill in what we know. We know nothing about B. B is just B over the sine of B. We don't know anything about those angles, right? And we know that side C is 10, and that the sine of C we don't know. So out of these, which ratio are we going to pick to solve first? Well, I think we'll pick A because it's solved, right? And we'll set that equal to C and figure out what angle C could be. Let's scroll down a little bit here. So if we have 9 over the sine of 60, oops, 9 over the sine of 60 equals 10 over the sine of C. And we're going to do cross multiplication, right? So we'll do this. And we end up with the sine of C equals 10 times the sine of 60 over 9. Okay, we kind of covered this right at the end, so right before we left on break. But if you solve for the sine of C, so if we type this in our calculator, I don't think I have this written down anywhere. No, I don't think I wrote it down. So we'll have to put it in Desmos. So if I have ten times the sine of 60, right, divided by 9. We can put our 10 up in there if we want, right? We can put our 10 in the numerator. And then I have to remember, well, first of all, it's nice because I get a negative number that I'm in radians. So I get this number 9.62222, and that is equal to the sine of C. Okay, so it's 0.9, whatever that number is on there. So if I want to solve for what angle C is, we're actually going to use the inverse sign. So remember, we kind of did this right at the end. So if I take this and I actually take the whole value, nope, I want to go back over here and take the inverse sign of this, and I end up with 74.21 degrees. Okay. So C is, if I make my paper a little longer here. That's not what I wanted to do. C is 74.21 degrees. Okay, so everybody track along with that so far. How do we figure out C? Okay, cool. So now when I go back up to my picture, 74.21 degrees is C. Which case does that look like? These are horribly messy, so I apologize. Does it look like this one or this case? This looks like the second case, right? This looks like it's possible this could be 74.21 75.21 degrees. Okay. How do I figure out my other angle? So how do I figure out if there's another angle over here that it could be that's an obtuse angle? So the way that we actually do that is by taking whatever value we found and we take 180 and subtract it from that. So if I take 74.21 degrees, okay, and I do 180 minus 74.21 degrees, I end up with 105.79 degrees. Okay, so this is actually the second possible angle that I could have for my triangle, 105.79 degrees. 105.79 degrees. Now, why is this also true? Well, if you actually take the sine of 74.21 degrees and the sine of 105.79 degrees, you actually will get the same value. So if I take the sine of 74.21 degrees and I take the sine of 105.79, you can see that the values are the same. And that's just because of the nature of a sine curve. If you remember a sine curve, it's, it has this repetitive nature. So to find the other possible value, we take 180 degrees and we subtract from that, because that the way the sine curve works, it's over every pi periods that it would repeat. Okay, everybody's so far so good? So now we have established that there actually are two possible triangles that meet this criteria. And we're still not done yet. But wait, there's more. We have to figure out B, right? We got to solve for B. So we have two cases, and the kind of the mathematical way that you would write this. What am I doing? The mathematical way that you would write this is you could call this C sub 1, and this could be C sub 2, because they're both C, right? They're just two different values. So C sub 1 and C sub 2. C sub 1 and C sub 2. So now I want to figure out what B is. So you'll notice when I wrote my ratios out, my proportion out, right? I have B over the sine of B, and I don't know what either one of those are. So I need at least one of those to figure out what the other one is. I can't have two unknowns. I have to have one solved. So which one do you think we can solve more easily? B or side B or angle B? Angle B, right? Yep. Because don't forget that even though it's not a right triangle, they still add up to 180 degrees, right? So in my obtuse case over here, we have 60 degrees and 105.75 degrees. So that if I take 180 and I subtract those two, I end up with my little angle up here. My B1 angle is 14.21 degrees. Okay, so I did 180 minus 60 degrees minus 150 degrees, 105 degrees, not 150 degrees. Okay. In my acute angle, my second one, I have 60 degrees and 74.21 degrees. And that leaves my last angle as B2. I get 45 degrees. About. It seems like it should be more accurate. 45.79. There we go. That's better. 45.79 degrees. Like it shouldn't just be 45. Okay, so then if we have the angle, then the last part, solving for B, should be pretty straightforward, but we have to do it twice, right? So for my first one, my obtuse, I would say 9 over sine of 60. That's my side A. And then side B over the sine of 14.21. Okay, and then you would do some multiplication, cross multiplication, and I ended up with B for this one is 2.55, which makes sense, right? This B in this picture is really small. It's like a really small side, and that's what makes it an obtuse angle here. And I should say this is B sub 1. Okay, then I could do the same thing for B sub 2 and solve for that. So when I solve for B sub 2, I end up with 7.45, which also seems reasonable given my angles. So that's basically the law of sines when we have an angle and two sides. That's when you can end up with a case where you have more than one possibility. So now that we've kind of solved it and kind of worked through it, when you look at this chart that's on the first page, if I can get my mouse to come up, it kind of tries to describe what are the different possibilities. So consider a triangle for which you are given A and B, sides A and B, and angle A. Okay, so you could have a case where you have this angle, right? And you have side B and side A, and there's no possible solution that would give you a solution. So it is possible that you can't make a triangle with that given value. You could have a triangle where you put in B and A, and you get one possible solution, right? Oh, sorry. This is if A is an acute triangle. I'm sorry. If you have an acute triangle, you could have one possibility this way, one possibility this way. You can have a case like that we just did where your second value could either make the triangle acute or obtuse. Right? This is our 2 case. And then we have some other cases where you get no solution. So basically, you have to work through the problem, think about what you think the triangle is going to look like, and come up with, do you think there's 2 possible solutions, 1 possible solution, or no possible solution to the triangle? Okay. So let's do 2 more examples in here. And I don't even know if we're going to finish because I know Jennifer had a couple questions. So let me just do these 2 examples quick. And then there's a little thing about the area, how we can find the area, but we'll probably just do that on Thursday because I know you guys have a lot on your plate finishing up chapter 5. So I don't want to overwhelm too much. So let's just I want to do 12 and 18, and we might not work through all the parts of 12 and 18, but I think you'll see this kind of gives us the different cases. So 12 says, we have an angle B that is 2 degrees and 45 minutes. So let's just go ahead and translate that to 2.75 degrees. I'm going to have a lot of fun drawing that. Side B is 6.2 and side C is 5.8. It's going to be a lovely, lovely triangle for me to draw, right? So if you have angle B, and I just always start from here. So if I have angle B is like 2.75, that's like this. I mean, it's smaller than that, right? So this is B, and we know it's 2.75. And we know that side B over here is 6.25. Okay. That kind of looks like a B and a 6. So let me fix that up a little bit. $6.25. All right, so then we can just pick our random C. So C is almost the same size as B, and I've drawn my picture, and C is nowhere the same size as B in this picture, right? So let's see. We'll make this angle C and this angle A. So this is side A and this is side C, and they're 5.8. So my picture is complete. I've already realized that my picture is completely inaccurate, but let's see if the math will save my picture, right? So I know my law of sines, A over the sine of A equals B over the sine of B equals C over the sine of C. So let's just kind of fill in what we know. We have A over the sine of A. I don't know anything there, right? I know B is 6.2 over the sine of 2.75, which equals C, which is 5.8 over the sine of C. Okay, so then I don't know anything about A, so I'm going to have to go with C, solve for the sine of C. So if I write this out, I'm going to end up with the sine of C equals 5.8 times the sine of 2.75. This is by cross multiplication, right? Over 6.2. And if I do my calculations, I end up with C equals 2.57 degrees. Okay, so what I did is I took the inverse sine of both sides. And again, I'm taking a couple quick steps here just so that we can kind of get through everything. And that makes sense, right? That those side C and side A, or no, side C and side B are really similar in size, so it would make sense that our angles are the same size. Okay, so we need to see if there's a second case. We need to see if there's a second case for side. So this, we'll call this C1, right? So let's see if there is a C2. So C2 would be 180 degrees minus 2.57 degrees, right? So that would be 100, no, yeah, 100 and, sorry for my writing on here, 177.43 degrees. Okay, so far seems like it's possible to have a C2 that big, but let's see. So then let's keep going here. If B is 2.75 and C1 is 2.57, then what is A1? I should have left a little more room here. Just trying to make this bigger, sorry. Oh, look at all that room I have over there. So I have B, I have angle B, I have angle C1. So if I add those together and I subtract from 180, I get angle A1 would be 174.68 degrees. Okay. In my second case, if I have 180 degrees and I subtract 177 and 2.75, I end up with angle 2 equals negative 0.18 degrees. So what I'm saying is that if I add up, or if I take 180 degrees and I subtract angle B and I subtract angle C2, I end up with a negative value for angle A. So is the second case possible? Can we have a negative angle? Nope, right? Can't have a negative angle. So we know in this case, there's not two possibilities for the triangle. There's only one possibility for the triangle, that we have angle B is 2.75, angle C1 is 2.57, and angle A is 174.68 degrees. And then we can go from there. Once we have that, we can figure out what side A would be. If you'll give me 1 second, I want to try to pull something up. Oh, and I can leave my microphone on. There was a really cool website that I was using for geometry. It's like Desmos for geometry. No. It was like Geo World or something. No, that doesn't seem right. I can spell. Graphing lines and angles. Oh, I can't find it that quickly. There's a really cool website that lets you graph these triangles really easily. So I was thinking, oh, well, that would be really cool to do. But I cannot find it. So if I find it, I'll send it out to you. So let's try to draw this triangle now that we have this data. And it's a total mess, so I apologize. So angle A is 174 degrees. Angle C is 2.57 and angle B is 2.75. So this triangle is basically going to be one of those triangles that looks almost like a line, right? It's going to be like this, but much more pronounced because these are only 2 degrees or 2 to 3 degrees, right? And this is your really big angle. So what would you expect the size of side A to be? It would be pretty big, right? It would be your largest side. Okay. I think we should probably stop there so I can get to your questions, Jennifer. Like I said, I'm sure you guys are probably working on finishing up your chapter 5 stuff, so I don't want to get too much into that. So we'll have time on Thursday to go over some more things because there's a few more things in 6-1. All right. Jennifer, you said the last, where are we at? Let's see if I can get the chat. Number 9 and number 11 from 5-5. Okay. It says, use a graphing utility to approximate the solutions of the equation over the interval. If possible, find the exact solutions algebraically. Okay, so let's start with number 9. Let's start with graphing it to see what we're looking at, right? So now I think I need to switch back to radians. And I have the sine of 4x. And I have on the other side of my equation, this is number 9, -2 sine of 2x. And I am over the period from 0 to 2 pi. And I'll step by pi divided by 2. Sure. Okay. So what are all the solutions to my equation? Where do I intersect at? Oh, this is weird. It's not giving me my intersection points. Just letting me pick one or the other. Huh. Okay, well, here we go. Oh, that's odd. Usually it gives it to you in, I wonder if it's because I put this in here. Huh. Maybe because I went to degrees, it kind of changed it up. But it looks like we have, what would that be? Well, I guess we'll have to figure it out algebraically, and we'll look on the graph to see what that looks like. Definitely we have pi. I think that's pi over 2. Yeah, that's pi over 2 and 3 pi over 2. Yeah. Okay, so we have that established, even though Desmos is not giving it to me in radians. So then let's go and try to mathy-wise, algebraically, right? Let's try to see if we can solve it. All right, so this is number 9. We have the sine of 4x equals the negative sine of 2x. Okay, so let's get everything on one side of the equation. All right, so let's do the sine of 4x plus 2 times the sine of 2x. And that equals 0. So at least we have 0. I feel like since we are in the double angle formulas and we have 4x and sine of 4x and sine of 2x, we can't combine those together. But if we simplify the sine of 4x, if we took the if we use the double angle formula, then we could end up with sine of 2x and we might be able to factor something. So what I mean by that is we have the sine of 4x right here, right? What if we think of this as the sine of 2 times 2x? And then that way we can have two values that both have the sine of 2x in it. All right, so if I think of this and use the double angle formula, I can rewrite the sine of 4x as 2 times the sine of 2x times the cosine of 2x. Now we added a cosine in, but at least we have we're all in 2x now, right? Okay, so now I actually have something that I could factor out, right? I have 2 sine of 2x on both sides of my equation. So if I factor that out, I get, or both terms of my equation, 2 sine of 2x times the cosine of 2x plus 1 equals 0. Okay, so now I can set both sides of my equation equal to 0. So let's see if we can get anywhere with this, right? I wonder if I have to double angle formula again, is what I'm thinking. Double angle my double angle formula. I don't know if I like that. So let's just see what we can do here. So if I set 2 sine of 2x equals 0, right? That means that the sine of 2x has to equal 0. And if I just think of 2x kind of as a whole unit, where does the sine of something equal 0? The sine of something equals 0 is at pi, right? Or at 2 pi. So if I'm looking at my unit circle. So I know that if I made x equal to pi by looking at my unit circle, right? The sine of 2 pi equals 0. So, and then if I go refer back to my graph, that is one possible solution. All right, so now let's look at the cosine. So we have the cosine of 2x plus 1 equals 0. Okay, and I have the cosine of 2x equals negative 1. So let's look at this again like a whole unit. If I look at this like a whole unit, like if I call this, I don't know, theta equals 2x, right? The thetas that give me a cosine of negative 1 are at Oh, wait, guys, I did that wrong. Me and my sine and cosines, right? The cosine of theta equals -1 when theta equals pi, right? Oh, no, I did it right. Sorry. When theta equals pi. So if theta has to equal pi for the cosine of pi to be -1, that means that 2x has to equal pi, or that x has to be pi over 2 for that to be a valid value. So then how do we get to 3 pi over 2? 3 pi over 2 is just the next iteration of the cosine of pi. So I think we just kind of assume that based off of our next value. That would be our next iteration of, yeah, 3 pi would also give you -1. So it's our next iteration. Okay, so that's 9. Does that help, Jennifer? All right, cool. 11. Let's tackle number 11. Okay, 11 is the cosine of 2x plus the sine of x equals 0. So let's see what our graph tells us. This one seems like it's going to be easier, but I don't know. I shouldn't say that without doing it, right? Cosine of 2x equals, oh, no, cosine of 2x plus the sine of x. Where does that equal 0? That's a crazy looking curve. Still don't know why. It's in radians. 0 to 2 pi is what we want. I must have been messing with it. 0 to 2 pi. Okay. So it looks like, oh, pi over 2, 7 pi over 6, and 11 pi over 6. So we kind of have the two curves that are competing with each other, right? So let's figure this out algebraically, see if we can figure out what's going on here. So we have number 11, cosine of 2x plus the sine of x equals 0. All right, so I feel like with this, I have a single sine of x, and then I have the double 2x, cosine of 2x. So what I want to use is I want to use the double angle formula for the cosine so that I at least end up with like a sine value that I can work with. Okay, so for the cosine of 2x, I'm going to just use the straight double angle formula, and I'm going to substitute in instead 1 minus the sine squared, no, 2 sine squared of x. So I need a 2 out here. 2 sine squared of x plus the sine of x equals 0. Okay, so let me rewrite this a little bit. I'm going to write minus 2 sine squared of x plus the sine of x plus 1 equals 0. And this looks like a whole lot of like something that I probably should be able to factor, right? If you wanted to, you could change everything. Like you can make it a positive 2 and a negative sine of x and a negative 1 also. I think I might actually do that. So I'm just going to change the signs of everything by dividing by -1 or multiplying by -1. Okay, so now I want to factor this. Okay, so I know I have a 2 sine of x, and I have a sine of x. And I have a 1 and a 1. And I know that my middle term needs to be negative, so I need this to be bigger and this to be smaller. So if I factor it out, then I end up with 2 sine of x plus 1. times sine of x minus 1 equals 0. So then I'm going to set each factor equal to 0. So 2 sine of x plus 1 equals 0. So I end up with sine of x equals negative 1/2. So if I go to my unit circle and I look for negative 1/2 for the sine, that is where I see that my x could be 7 pi over 6. And it can also be 11 pi over 6 also. 11 pi over 6. Okay. And then if I take my second side and I get, this comes out to be sine of x equals 1. So where does the sine of x equal 1? I have sine of x equals 1 at pi over 2. So then I forget, did that check out with what we said? Pi over 2, 7 pi over 6, and 11. Yes, those are our 3 points. All right, so I think that's it. Any other questions? Everybody got the test okay? Oh, I do want to mention, oh, yep, I'm sure. So, there we go. This should be a 1 here. It's kind of getting messy. I do want to mention, in case you didn't look at the test yet and you're studying for the test before you open it, there is a reference sheet that I sent over with the test on the first page. So I did give you a unit circle. I gave you the half angle formulas and the double angle formulas, as well as I have it sitting right here. I gave you the half angle, double angle, and the sum and difference formulas, and a few of the Pythagorean identities. So you do not have to memorize the sum and difference formulas and the double and half angle formulas. So just so you know, if you don't open it up and you're studying ahead of time and you're trying to memorize all those, I'm not requiring you to memorize all those. Yeah. So, all right. Well, thanks for coming and joining on today. Hope you guys all take care, and we'll talk on Thursday. Thanks, guys. Bye.